Hello and welcome to the first episode of a series in which we're going to cover data structures. Today we're going to focus on lists. I'm going to try my best to explain everything clearly and in detail so you don't need any prior knowledge in the subject. However, I will assume that you're familiar with the basics of object-oriented programming. We're going to learn the overall concept of linked lists, the reasons to use them, and we're also going to take a look at a few different variants of lists. Finally, we're going to implement a list in pseudocode close to C#. Alright, I assume you're familiar with simple variables and types, such as these. Now, let's have a real-life reference because it's always easier to learn abstract topics on a more palpable example. Imagine you need to make a shopping list and you want to write a program for it. You could start with a simple string item variable, but wait, what if you need to buy 2 items and not just one? Well, you could obviously make string item 1 and string item 2 variables, but let's be real, if you only need to buy 2 items, chances are you don't need to make a shopping list at all. Let's scale it up and say we want to keep a list of 10 items. You can probably tell that the approach with using individual variables for each item is beginning to look bad. And still, we can't tell for sure how many items are going to be on the list. Even if you make 20 variables, you may one day want to buy 21. And what if after adding 20 items to the list, you decide to cross off items number 5 and 7? How are you going to manage the gaps? You could easily improve the code's readability by using an array instead, but we still don't know how big the array should be and how we'd handle crossing things off in the middle of the array. And that's why we need a better data structure. So let's have a look at a real-life shopping list. In life, you'd probably take a reasonably sized piece of paper and start writing down the items. Sometimes it'll be 4 items, sometimes 25, but an average piece of paper should always be enough. You don't take individual pieces of paper for each item, do you? And when you need to cross things off your list, that's completely fine. You just ignore the removed item, and when you need to add something else to the list, you write it at the bottom. If you were using a separate piece of paper for each item, or in code separate variables, you'd have to decide what to do with removed items, and you'd waste a lot of paper. Alright, so we know what the goal is. Instead of writing things individually, like here, we'd like to create one variable that can contain as many items as we need. We can add elements to the list at any time, always attaching them to the bottom, so that the items are stored in the original order, and when we decide to remove one of the items, we can easily do that, keeping the rest of the list intact. By the way, if you look at the syntax I used, this is what you'll likely see in languages such as C# or Java. Lists are often available in standard libraries, and their implementations let you use them with objects of different types. So you can make a shopping list with names of items, you can make a list of numbers, letters, and so on. However, before you use the lists mechanisms provided to you by some libraries, it's good to first learn how lists work and implement one yourself. We're going to implement a list in a simplified version, and because we're making a shopping list, we're going to store string elements. The final result will look like this. We'll define our list as list shopping list, and then we'll have 2 methods available, add and remove, for, you guessed it, adding items to the list and crossing them off. So let's once again look at a realistic shopping list. It contains multiple independent items, but they're all connected in a sense that they're inside the same list or on the same piece of paper. Now, let's consider the individual elements. Each of them needs to have a name so that we can actually store names of the items to buy. The second thing each element knows is where in the list it's placed. We'll solve this issue by keeping an information on what elements comes afterwards. So we have a string name and a link to the item that's next on the list. So the first element in our example has a name milk and a link to the second item. The second item has a name bread and a link to the third item. And the third element has a name cheese, but its next reference is empty because there's nothing else on the list. Okie dokie, so let's put it all in code, starting with the base class for individual items. We'll call it a list node. We've already established that it needs to have a name, string name, and that it knows what comes afterwards. And because all elements are of the same type, just with different names assigned, the next property is the same type as our list node, in which case it looks like this. So now let's have a look at the class that will wrap all of the individual items in a single list. We're going to create a class and call it a list, and inside that class we're going to have a list node head. A head of a list is how you commonly refer to the first element of a list, so the item that's written first on top of a list. And if you remember that from each element you can easily get to the element after it, thanks to the next reference, keeping track of the first item of the list is all we need to be able to access every other element. You may also choose to store another reference to the tail of the list. A tail of a list is the last item of a list, so the most recently added element. It's not necessary to keep this reference, but it does make adding items to the end of the list easier. You'll see the difference in code as we're going to implement a list with and without keeping the tail reference. Alright, so we know that the list knows about its first and optionally last element. Now, we also need to be able to use the list. In particular, we may want to be able to add items to the list and remove them. We're going to need to implement both operations. We're going to assume that we always want to add items to the bottom or to the end of a list, and that we can cross any item off regardless of where in the list it is. We're going to implement both operations in two variants, keeping only the reference to the head of the list, and second with both the head and tail reference. Let's start with adding items to the list when all we know is the first element of the list. First, we create a new node with the given name, and now we need to attach this node to the end of the list. For that, we have to consider two options. First, when the list is currently empty and there's no first element. So, when the head of the list is null, we want this newly created element to be the head of the list. Otherwise, if the list already contains elements, we need to find the last element of the list and append the new node after it. For that, we're going to jump from the first element to the second, through the next reference, then from the second to the third and so on, until we find a node from which there's nowhere to jump to. That's when we'll know we've reached the end of the list. We're going to start at the head of the list, so we're going to copy the reference to the head of the list to this current variable. Then, for as long as there's a next element to jump to, we're going to move forward. You can see it in the example on the right. With each step of the loop, we moved the current element one step towards the end of the list. Then, when there's nothing to move to, the loop terminates. So we know what the last element of the list is, and now we want to attach the new node to it, so we can say current.next equals node. And that's it, the first method done and dusted. Now, what if we wanted to add an item to the list, but in addition to the head of the list, we also knew the tail? The beginning is the same, we need to create the new node. If the list doesn't yet contain any elements, we make the new element the head of the list, but also the tail of the list, because if a list only contains one element, that element is both the first and the last. Adding a new item when the list already has some elements becomes much simpler when we know the tail of the list. Here, we simply need to say that after what used to be the last element until now, comes the new node. And then we need to remember to update the tail reference, because now the new element is the last on the list. Keeping the reference to the tail of the list lets you skip traversing the whole list upon adding a new element, which is especially helpful when the list gets long. For example, instead of jumping through 1000 elements just to append one new node, you simply append the new node to the tail. Alright, we're halfway through the implementation. We know how to add items, and now we want to be able to remove them from the list. Again, let's start with the case in which we only know the first element of the list. The first thing we need to check is whether the list contains elements. If it doesn't, or in other words, when the head of the list is empty, you know for sure that you're not going to find the item you want to remove, so our job is done here. Next, if the item we want to remove is at the start of the list, we want to make the second element our new head of the list. And finally, in case the element is somewhere further in the list, or not in the list at all, we need to traverse the list the same way we did when we wanted to find the last element when we were adding a new item to the list. We're going to start at the head of the list and keep jumping to the next element until we reach the end of the list, or until we discover that the next item we jump to is the one we want to remove. So in the example on the right, you can see the item we're looking for doesn't occur in the list. In this case, we reach the end of the list and the loop terminates. In the second example, we start at the head of the list and check the next element. It does exist, and it's not the one we want to remove, so we jump to it. In the second pass of the loop, we're at the second element, bread, and inspect the element after it. It's not empty, but it is the item we're looking for, eggs, so we don't jump to it, we stay at the bread element. And now, looking at those two examples, we can say that if the next element is empty, it means we haven't found the element to remove and therefore don't have to do anything, or if the next element does exist, it's the one we want to delete. In this case, we want to connect current element, bread, with whatever comes after the item we're removing, so in this case we want bread to lead directly to flour. We do that by writing that the next element of current item is the next element of the next element of current. So current is bread, old current.next is eggs, current.next.next is flour, and we're overwriting eggs so that current.next is now flour. Alright, I hope that's clear. Now the last method to implement, removing items from a list where we know of both the head and the tail. The beginning is the same, we check if the list is empty and if so, finish the algorithm. Then, if the item we need to remove is the head of the list, we move the head to the second element, just like we did before. However, in this case, we need to check one more thing. If the list originally had just one element and we're now removing it, after moving the head by one element forward, the new head is now empty, which means the list contains no elements. In this case, we need to clear the tail reference too, because when the list only had one element, it was both the head and the tail of the list, and now with the list being empty, both head and tail should be empty. Alright, and now the last case, when the element's somewhere further in the list, or not in the list at all, we traverse the list the same way we did before. So we either end at the end of the list, not having found what we are looking for, or we stop just before the item we want to remove. And again, if the item to delete doesn't occur in the list, we don't need to do anything, so we're only going to look at the situation where the next element isn't empty, and it's the one we're removing. We start by skipping the item and connecting the current element with what comes after the one we're deleting. But now, we need to be careful when doing that. And again, we now have two options, you can see them on the right. The element to be removed may be in the middle or at the end of the list. When we update the link in our current element, bread, to skip eggs, we're left with a situation like this. If the removed element was in the middle of the list, everything's fine. However, if it was the last on the list, we now need to update the tail reference. So if after current element there's nothing else, the current item is the new tail. Alright, we've reached the end of the implementation, I hope it was clear. Now, just a few words. There are many different possible implementations of a list. You may or may not keep the tail reference. You may decide to add items to the start of the list rather than append them to the end. You may add your own terms and conditions depending on what you want to achieve and what suits your needs best. And a few things to watch out for would be, first of all, for all operations on a list, it's good to remember that the list may be empty. Secondly, you may want to handle duplicate values in a certain way, for example, not allow them at all, or, while removing items, you may want to remove all items with the same given name, not just the first one. And finally, whether you keep the head or tail reference or any other links, you need to remember to update them when necessary. Now, speaking of different implementations of a list, the one we've implemented is commonly known as a singly linked list. This means that there's only a single connection between two consecutive elements. In our case, from the first element you can access the second one, but not the other way round. The variant in which you can traverse the list in both directions is known as a doubly linked list. Here, in each element, you have a link that takes you to the next item, but also you have a link that can take you to the previous one. So in code, on top of the list node next property, you'd also have a list node previous one. And the third interesting option I'd like to show you is a list that creates a loop in which the last element, instead of pointing to nothing, takes you all the way back to the start of the list, and this is known as a circular list. And finally, the last important thing to talk about while learning data structures, the main point of studying them is to eventually be able to decide what data structure will best suit your needs in a particular situation. We've implemented our list in two different variants, and hopefully you were able to spot the difference in efficiency. With the tail reference, so knowing the last element of the list, we were able to quickly insert a new element at the end of the list, and the speed of this operation didn't depend on the number of items already in the list. However, knowing only the head of the list, we had to always traverse the entire list when appending a new item. This scales quickly, so it's good to have it in mind. Deleting an item is also simple. It only requires updating the link from the previous item to make it skip the item being removed. However, in order to delete an item, we first had to find it, and that, worst case, required us to go through the entire list, possibly for nothing if the item didn't exist at all. In terms of space used, in order to store 10 items, we need to use 10 string name variables, one in each element, but also 10 links to next elements on the list. So a list of 10 elements uses more space than, for example, an array of 10 elements. In this case, if you need a data structure that will store exactly 10 elements, or any other number that you know will always be the same, perhaps you should use something like an array. However, if you're not sure about the number of items you'll need to keep, a list may be a good choice. Now, the speed of operations and the space used can actually be formally described with a big O notation. We're not going to delve into it today as it's a complex topic in itself, but if you'd like to learn more, it's an important subject and it's worth giving it a read at some point. And by the way, we said you can implement your list in various different ways. You could, for example, decide to add and remove items only from one, the same end of the list, and this structure actually has its own name and it's a stack. Or, if you'd like to add items to one end, for example to the bottom of the list, like we did today, but only remove them one by one from the start, then you'd create a queue. We're going to talk about both stacks and queues in future videos. And for now, thank you for watching if you made it this far, and goodbye.